Hey, what's up, guys? Yeah. So in this video, I want to talk about a very small lemma, or basically, one application of this second moment method. Right. So in the probability that the second moment method basically is saying that you want to know the probability of x with some constraint, right? With some constraint, like Chebyshev inequality with some constraint, using due to or using the second moment. Okay, and there's a contrast. Basically, there's a okay, and probably this kind of the simplest first moment method is basically the Markov inequality. Okay, and Markov inequality is very simple, right? So let's say you have a probability, you have a random variable greater or equal to 0, and you want to know that the probability of x greater than a, right? Let's say how to bound this guy. It's basically bounded by its potential value is divided by a. Okay, so this is Markov inequality, and you can check the proof. It should be very simple. You can try to prove it by yourself. Basically, you can prove this by just one line. You can yeah, it's not difficult. Okay, and there will be some difficult one or Chebyshev called Chebyshev inequality, or Chernov bounds, or Hofstad inequality. Basically, they are using the second moment. So there's an idea called second moment method. Okay, so today I want to prove another one. Basically, it says that if you have x greater than 0, and but you really want to know the probability of x greater than 0. Okay, so I want to bound this by below, right? Because suppose I know x greater than 0, right? So I basically immediately know that the probability of x greater or equal to 0 is 1. But I want to know that how do I control this probability x greater than 0? 0 says that the probability of x greater than 0 is basically bounded below, right? So this is non-trivial, right? Gives you the upper bound. As it gives you a lower bound, it's expectation value of x squared divided by expectation value of x squared. Okay, so basically, if you know the first moment and second moment, and then you can bound it the probability of x greater than 0. The proof is one line. So maybe let's prove the Markov inequality first, so that you understand the trick. So let's prove the Markov inequality. So if x equal to 0, I want to know that probability of x greater than a is bounded. That's this one, right? Also, the proof based on the proof. What I want to prove will be write the probability as the exponential value. Right, so I can just write the following. Okay, I can just say x times 1, x greater or equal to a. So this is the random variable, right? 1, this means that x greater or equal to a, I assign 1. So this guy is a random variable, this guy is a random variable. And then for each possible random variable, this guy is bounded by a, greater or equal to a. Okay. Because when right, so let's see. Let's see what's going on. Let's see. Right. So x1, x greater than equal to a. Oh, sorry, I'm stupid. I guess I write a different. Should be here. Let's see, it should be here. X1, x greater than equal to a. Okay, so notice that right. So if x is greater than a, then this will be x, right? This will be a, right? This will be a. Okay, and okay, so this means that if x greater equal to a, then this is x, this is a, right? So obviously greater equal to. If x less than a, then this will be still be x, and greater equal to 0, but this guy will be 0. Right, so this equation is true in general, right? So you can take the expectation value. So this becomes expectation value of x greater or equal to a, and the expectation value of this. This is just probability of x greater or equal to a. Right, so if you shift this a to the left hand side, then you prove this Markov inequality. Okay, so now go back to the proof, right? Go back to this one. So the goal is to write this guy as the expectation value, right? So this is the general idea. So I can write my probability of x greater than 0 to be just 1, x greater than 0. Okay. Now notice that I can write expectation value of x as expectation value of x times 1, x greater than 0. Right, so this is a random variable, this is a random variable. And then notice that second moment tell you that the expectation value of u squared, expectation of v squared, will greater or equal to expectation value of uv squared. Okay. So this is basically Cauchy-Schwarz, or basically you can say, oh, this is just, you can prove it. Yeah, it basically is just Cauchy-Schwarz. So this is less or equal to expectation value of x squared. And then this also this characteristic square. Characteristic square is still characteristic. So it's expectation value of 1 x greater than 0. Okay, and this guy is basically probability of x greater than 0. Okay, so you immediately prove that the probability of x greater than 0 is greater or equal to expectation of x. Oh, notice that there's a square here, right? So you take a square. Okay. So now you square it, so you get this. Okay, so yeah, so this is the proof. Okay. So this kind of idea, the proof basically using the similar as the Markov inequality and but related to the second moment. Okay, see you guys next week.